Hi, today we're going to solve an interesting equation. The equation is x cubed minus 3x equals the square root of x plus 2. And we want to find real valued solutions for x. Now, along the way, we're going to make a trig substitution, which will then lead to having to use some trig identities. They're not perhaps so well known, although they are used. And the first one is cos of 3 theta equals 4 cos cubed of theta minus 3 cos theta. And the second one is cos of theta plus 1 is 2 cos squared of theta over 2. Okay, so where should we start with this? Well, first we notice that there's a restriction here with our radical. X plus 2 has to be greater than or equal to 0. So let's take note of that first. Our radicand must be 0 or positive. But if that's the case, then that just implies that x is greater than or equal to negative 2. Okay, great. So any solutions we find for x have to be bigger than negative 2. But also by inspection, notice the following. If we substitute 2 into the equation, does that solve it? In fact, it does. So 2 is a solution. Well, then why don't we do the following? If we know our solutions have to be greater than or equal to negative 2, and at 2 we already have one solution, let's look between negative 2 and 2 to find any other solutions. So case number 1. We'll look between negative 2 and 2 for x. But here's where we're going to make our trig substitution. We're going to let x be 2 cos of theta. But how do we ensure that 2 cos of theta remains between negative 2 and 2? Well, cos of theta equals 1 if theta is 0. And cos of theta equals negative 1 if theta is pi. So cos of 0, that's 1, times 2, that's 2. And then cos of pi is negative 1 times 2 is negative 2. So if we make sure to keep theta between 0 and pi, then 2 cos of theta will remain between negative 2 and 2. Okay, perfect. So now that we have this statement, let's substitute 2 cos theta in for x into our equation. So we have 2 cos of theta cubed minus 3 times 2 cos of theta equals the root of x plus 2, or 2 cos of theta plus 2. Perfect. Well, we can clean this up a little bit. This quantity cubed is 8 cos cubed of theta. Distributing the 3 gives us 6 cos of theta. And then factoring out a 2 from inside the radical here, we get 2 times cos of theta plus 1. Here we can factor out a 2, leaving us with 4 cos cubed of theta minus 3 cos of theta equals, and we'll just leave the right-hand side for now. But here's the nice thing. 4 cos cubed of theta minus 3 cos of theta, that's just this identity right here. So we can replace this with cos of 3 theta. And on the right-hand side, we also have cos of theta plus 1. but that's this identity here. We can replace what's in the radical with 2 cos squared of theta over 2. But now, under the radical, we have 4 cos squared. Taking the root of that leaves us with 2 cos of theta over 2. So 2 cos of theta over 2. Now that allows us to make these annihilate each other. And we're left with cos of 3 theta equals cos of theta over 2. Well, now here, we have to be a little bit careful. Certainly, this side has to equal this side. But it's not just that 3 theta equals theta over 2. In fact, when we take the arc cos of both sides, or the cos inverse of both sides, what we end up with is the following. Arc cos on the left side gives us 3 theta plus an integer multiple of 2 pi. And on the right-hand side, because cosine is an even function, we can have plus or minus theta over 2. So taking the arc cos of both sides leaves us with not just 3 theta on the left, but plus an integer multiple of 2 pi. And on the right side, because cosine is an even function, we have plus or minus theta over 2. But now that we have that, this breaks up into 2 parts. Part A gives us 3 theta minus theta over 2 equals negative 2 pi m. And in the second case, we have 3 theta plus theta over 2 equals negative 2 pi m. So here m is some integer. Well, let's solve each of these in turn. First of all, from A, multiplying all through by 2, we have 6 theta minus theta equals negative 4 pi m. That just tells us 5 theta equals negative 4 pi m, or theta equals negative 4/5 pi m. Well, we need theta to be between 0 and pi. So what will ensure that here? What values of m? Well, if m is 0, then theta is, well, negative 4/5 pi times 0, that's 0. And that falls within this interval. How about if m is negative 1? Then what's theta? Well, negative 4/5 pi times negative 1 is positive 4/5 pi. 4/5 of pi is a little less than pi, so that does fall between 0 and pi. But then, if we pick any other lower integer, negative 2, negative 3, negative 4, what happens? Well, when m is negative 2, we get 8/5 pi. If we plug in negative 3, we get 12/5 pi. Those quantities end up becoming greater and greater than pi, and so we fall outside of this interval. So no more negative integers will work, but no other positive integers will work either, because any positive integer for m will give us theta that's negative, and that will fall outside this interval. So right now, we know that m is 0 and m is negative 1, and that provides us 2 solutions for theta. How about from B over here? Well, if we multiply through by 2 as well, we get 6 theta plus theta, that's 7 theta, equals negative 4 pi m. But all that tells us is theta is negative 4/7 pi m. Now again, If m is 0, we'll obtain the same solution as up here. If m is -1, well, we also obtain a valid solution. Why is that? Well, if m is -1, we have -4/7 pi times -1, that's 4/7 pi. Now 4/7 pi is less than pi, and it's positive, so it is between 0 and pi. But again, if we choose m any lower than -1, for example -2, then we hit 8/7 pi, that's a little more than pi. And then if m is even lower, even more negative, we'll step further and further away from pi. So we fall outside this interval. And again, if m is any positive integer, then theta is just some negative quantity. And that falls outside this range again. Okay, great. So what we end up with is theta equals 0, theta equals 4/5 pi, and theta equals 4/7 pi. So if that's the case, then what we have is the following. So far, x is then 2 cos of 0. 0 is one solution we have for theta. So our solution for x is 2. But also theta can be 4/5 pi. And thirdly, we can also have theta as being 4/7 pi. So x is just 2 cos 4 pi over 7. Okay, great. So far we have 3 solutions for x. But this is only in the interval for x being between -2 and 2. X cannot be less than -2, we know that already. But how about for when x is greater than 2? We need to check that case. So let's come back and see what happens. Okay, so we left off with case number 1, x between -2 and 2, and we found 3 solutions to our equation. Now let's look at case number 2, which is the only one remaining, when x is greater than 2. Well, we're going to take note of 2 important properties here. First of all, notice that x is greater than the root of x plus 2 when x is greater than 2. For example, you can sort of test this out. Let's pick a value greater than 2, such as 3. Well, 3 is greater than the root of 5, certainly. Or 4 is greater than the root of 6. But you can also see this graphically. Think of the function y equals x. That's just a line like this. And then think of the function, the root of x plus 2. That just looks something like that. And they meet here when x is 2 at a y value of 2. Beyond that, the linear blue function grows faster than the purple root function. So when x is greater than 2, this function is certainly greater than this. Okay, great. Let's also take note of something else. X cubed minus 3x is greater than x. Graphically, the function y equals x cubed minus 3x, well, that's an odd function that passes through the origin and looks something like this. X again is a linear function that runs through the origin like so. But these two graphs cross right over here at x equals 2 and a y value of 2. Beyond x equals 2, the orange function grows faster than the blue one. So this function is greater than x when x is bigger than 2. Well, now if we put this together, if this is bigger than x, but x is bigger than this radical, what we have is the following. X cubed minus 3x is bigger than x, but that's bigger than the root of x plus 2. But if that's the case, then we can't have any solutions where x cubed minus 3x equals the root of x plus 2, which is this equation we're trying to solve. They can never be equal because there's this intermediate value here where x cubed minus 3x always is greater than that, which is also greater than the root of x plus 2. So we have no solution. Perfect. So now we've checked all possible intervals for x between -2, which is the minimum value x can have, up to 2. And we found 3 solutions. Those were in case 1. So we had x equals 2, 2 cos of 4 pi over 5, and 2 cos of 4 pi over 7. And then we checked from 2 onward, but notice from this inequality that there can be no solution. So there we have it. These are the only 3 solutions that solve our equation up above. Thanks for watching.